All right, for this next video, we're going to look at problem set 4, which was just recently turned in. I posted this exact sheet on Canvas, but right now I'm just going to talk through some of the answers in case some people don't make it to lecture. I may talk about some of these again there. I'll be happy to answer any questions. But let's look at number 1. So it's asking which of these is the least acidic. So to consider acidity, a lot of times what is useful is to imagine deprotonating, in this case, the nitrogens. They'll be the most acidic hydrogens on the molecules, and considering the stability of the conjugate base. So we're going to be looking for the nitrogen or NH bond that ends up being the least stable. Things that are not very acidic will generate very high energy products on the other side. So in some cases, like for instance, maybe a normal amide, if we considered the deprotonated structure of an amide, we can see there is a considerable amount of stabilization of the nitrogen anion because we can have resonance delocalization onto this oxygen. So in one case, just sharing electron density is good. Putting it on an even more electronegative atom is even better. So this would be a stabilizing interaction. If we were only comparing two different amides, we would expect E to be more acidic than C due to the inductive effects of the fluorines. And we'd also expect that D is going to be more acidic than both of these molecules because it now has two carbonyls that it'll be able to put this electron density on. Now, whenever we go to options B and C, each of these molecules don't have any carbonyls next door, so we won't be able to put the negative charge onto another type of heteroatom. On the other hand, the aniline has two things going for it. One, it's actually going to be in a slightly different hybridization state. Usually anilines are a bit more sp2 hybridized, so they'll be a bit more electronegative. And then we also have resonance factors, where we have this aromatic ring that will be able to take some of the charge. And also the phenyl ring, which is sp2 hybridized as well, so it'll be a fairly electronegative substituent, being able to pull electron density out. Whenever you go to pyrrolidine B, this ends up being the least acidic. If we think about the nitrogen anion that forms here, this has absolutely no stabilization. The best comparison from the sheet of the numbers we remember is a pKa of 36 for ammonia. It actually might be a little bit higher than this still because of the alkyl donating groups that are present. So remember, we use things like sodium amide to deprotonate benzene rings to make benzynes. So this will almost certainly be the least, well, no, it will be the least acidic hydrogen of all. And this is sort of the way to think about it. Similarly, we can go look at acidity in a similar way. Things that are very acidic will make very stable conjugate bases. And so a quick way to go look at this is, how do the different types of molecules compare to one another? So we know that the pKa of carboxylic acids, these are usually starting around 5, and then we may have other effects from substituents like fluorines that may lower this further. If we go to something like a phenol, this is around 10, and alcohols usually start out around 16. So inductive effects will rarely make very, very large pKa jumps of 5 orders of magnitude, especially when the electron withdrawing groups are several atoms away. So this is a fairly long distance for an inductive effect to take place of any substance. So based on that, we would probably assume that no matter what type of alcohol it is, it's probably not going to be very competitive with 2 carboxylic acids. If we start looking at the amide, we could probably already start to see that this will be less stabilized, because while it will have resonance structures that can put the negative charge onto 2 different atoms, similar to carboxylates, one of these atoms is going to be a nitrogen, and nitrogens are less electronegative than an oxygen. And this brings us now back to sort of maybe our initial guess of the carboxylic acids will be the most acidic compounds listed. And we choose between B and A. And this comes down to small inductive effect differences. So while both have two fluorines on the molecule, B has the fluorines much closer to the negative charge that would be stabilized in the conjugate base, which is going to be on the oxygens. So in A, we have one fluorine that is farther away. The inductive effect weakens as it goes through sigma bonds. So these fluorines will be the best at stabilizing the negative charge of the conjugate base B. Now we're looking at which molecule will undergo hydrolysis fastest with sodium hydroxide. So we're looking at a nucleophilic attack directly on each of these neutral compounds. So we're looking at which one likely has, and in all cases, these all share carbon-oxygen double bonds. And based off of what we saw in the past section, the tetrahedral intermediates all have approximately the same energy level. It's all about the oxygen atom stabilizing that negative charge. And the rate differences come from how stabilized is the ground state. And this is usually demonstrated through resonance stabilization by donating lone pair electrons into the pi system. So now we need to try to evaluate which ones have the most resonance donation into the carbonyl and which ones have the least. In this case, nitrogen atoms are much better electron donors than oxygens. So right away, we would say that amides and ureas are going to hydrolyze much slower than something like a carbonate or esters. A carbonate has 2 oxygens, whereas esters each have 1. So we can also eliminate that answer as a possibility. And lastly, it comes down to A or B. So 2 esters both have pretty similar electron donating capability. The big difference ends up being the large steric bulk of these tert butyl groups. These will really block the attack of a nucleophile to make a tetrahedral intermediate. And this tetrahedral intermediate ends up getting larger anyways, which creates more steric shielding. So since we're looking at what would be the fastest, now we're actually going to have a steric effect come into play combined with the electronic rationalizations to separate the amides, ureas, and carbonates. So number 4 is a similar type of problem. So we're also trying to rationalize the electrophilicity of something. But now, instead of all of them being carbon-oxygen type molecules, we've added carbon-nitrogen double bonds into the system as well. So if we're looking for poor electrophiles, quickly we're going to eliminate things that are positively charged. These will be extra activated for nucleophilic attack. So we would really be thinking about any of these neutral compounds first. If we compare C and A, oxygen is more electronegative, so it'll have a more polarized carbon-oxygen bond relative to the polarization of a carbon-nitrogen bond. So we can eliminate A as one of our options. And then we're trying to compare C and E. And this is something that potentially I could have clarified a little bit better. So I accepted answer E as well on Gradescope, though it is not correct. But hopefully we can take some time to rationalize why this is the case. So even though this does have resonance stabilization that would slow down the attack, this type of effect is better in comparing similar carbonyl compounds, so things that have carbon-oxygen bonds. Whenever we switch to a carbon-nitrogen bond, things actually change quite a bit, because now we really are focused on what is the energy of an addition to a carbon-nitrogen bond. If we have a direct nucleophilic attack on an imine, we're going to end up with an amide anion. So this is akin to trying to deprotonate ammonia, something that's incredibly hard to do, or any sort of secondary amine. This is going to be very basic and very high in energy. And this is simply because a nitrogen isn't nearly as good at stabilizing negative charge as oxygen. So even though an ester will be slower than something like a ketone in an addition, it still ends up trying to get to an intermediate that is relatively accessible overall. So it really has to do with the stabilization of an O minus versus an N minus when comparing these two types of structures. But since trying to evaluate what is the effective electronegativity of an atom versus resonance effects, those are hard to probably rationalize without me telling you more about it, I decided to also accept E for this problem set. But going forward, let's try to think about things with some of these added considerations. Excuse me, I just choked on water. All right. So now we have just two, I think, sort of straightforward reactions that we learned in this section. One is dehydration of a primary amide with P2O5. This does a dehydration to give a nitrile. And then nitriles can be reduced with diabol, followed by acidic hydrolysis. This will go through an intermediate imine, but under the acidic workup conditions, it will be hydrolyzed by water. So at the end of the day, our answer will be D, the aldehyde. Sadly, number 6 we did get a chance to cover because of the truncated lectures, so we're not going to cover this. So here we're looking for which reaction will not give ethyl benzoate as a major product. Here we can see a lot of reactions we do know work to make ester bonds, such as the Fischer esterification. We have reactions of an acid chloride, which you know is very reactive and will react with ethanol to make an ester. And the combination of ethanol and DCC, specifically with DMAP, will also work to make an ester. The condition that does not work is catalytic sodium hydride. So you cannot make esters between acids and alcohols under basic conditions. Sodium hydride will simply go and make a carboxylate salt. And we have no way for a neutral ethanol molecule to be able to attack this to try to make a good leaving group out of that oxygen. So if we added in something like ethyl iodide, then we would be able to reverse the roles, but we need to have an electrophile present in order to use the carboxylate as a nucleophile. So since we don't have an ethyl electrophile, we only have ethanol, it's pretty much just going to deprotonate, and that would be your answer. We would not get ethyl benzoate out as a product. For number 8, we have methylamine. This is able to attack an anhydride. It goes through a tetrahedral intermediate and then kicks out a carboxylic acid. So after workup, we're going to end up with an amide that still has its leaving group attached. Here's the carboxylic acid. Methylamine won't be able to react further with a carboxylic acid. It might make a salt, but it'll mainly just sit there until it's worked up. Then we use lithium aluminum hydride in excess. Excess means that we have plenty to reduce both our carboxylic acid and our amide group. Carboxylic acids go to primary alcohols, and amides will go to a secondary amine. Note there aren't any neutral secondary amine options, so this must mean that we added a little too much of our acid in the workup, and we end up with B, this protonated ammonium alcohol, as the product. Number 9 is again a series of reactions. There are no tricks here, though we do throw in a little bit at the end from topic 2. In the first step, we use magnesium 0 to make a Grignard. This Grignard is able to react with carbon dioxide, followed by workup to give a carboxylic acid, and then thionyl chloride will turn the carboxylic acid into an acid chloride. So now we've made an acid chloride that we can use in a Friedel-Crafts reaction. Note the aluminum trichloride present. Also a anisole molecule, this methoxybenzene, that has a good electron donating group on it. This is an ortho-para-director. So we can see the ortho-para-directing groups. If we scan through the potential options, we don't see any ortho-substituted methoxy rings. We see one that is meta that we can cancel out as an option. We see a para one that ends up being the product. And all these chlorides are just there to kind of, I guess, throw you off. So 10 is a question that requires a little bit of thought, because our first inclination is that whenever we have a primary amine and we're reacting it with an alkyl halide, we're going to get mixtures of products. And that's because whenever we try to selectively make something like a secondary amine or a tertiary amine, we end up having over-alkylation problems. But this is a specific scenario where we end up with a whole lot of this ethyl iodide molecule. So since one of the issues is overreactivity, there is a point when amines can no longer react any further. So if we go through the process, you alkylate a primary amine, it turns into a secondary amine. A secondary amine will turn into a tertiary amine, and a tertiary amine will turn into a quaternary ammonium salt. After that, it can't go any further, it just stops. In order to affect these three reactions in a row, this means we're going to need to have 1, 2, 3 equivalents of ethyl iodide relative to our amine starting material. So you see we start with 4 equivalents of ethyl iodide, so we have more than enough to push it all the way forward, all the way to this quaternary ammonium salt. And that leaves us with D as the answer. So along the way we do make B and C, they just keep on reacting until you get to the dead end, that is D. For number 4, we have the Fischer esterification reaction conditions. We see catalytic H2SO4, we have alcohols, and we have carboxylic acids. Since each of these are bifunctional, they each have two carboxylic acids and 2 alcohols, we're going to make a polymer. And this is, of course, alluded to in the question which asks, what is the structure of the polymer? So when we ask for a structure of a polymer, what we're looking for is essentially the basic repeating unit, along with brackets and a little N down in the corner that represents this repeating over and over again. So from here you can see where we have the red portion, the blue portion, these are repeated. I'm going to get rid of these reds and blues real quick just so we can look a little closer at the chemistry. And so within the brackets, what we want to have is essentially the product of the reaction, which means we're going to be losing water along the way, so plus H2O. Usually this is driven away with the heat that's added. And that means we're going to end up having each of the individual atoms from ethylene glycol. So we have 2 carbons and an oxygen, and the other oxygen of this is on the other side. Oh, perhaps I'll make this blue just to go back and coordinate like I had before. So all of these come from ethylene glycol. The carboxylic acid loses its OH as water in the process, just like ethylene glycol lost one of its hydrogens. That means we're going to need to have exactly all of the molecules from the bis-benzoic acid. So we have all of the benzene ring and the 2 carbonyls. So we don't want to move this bracket over another atom. This would be incorrect, as would trying to have it in one more, because then we wouldn't have enough oxygens in the repeating units to represent the actual polymer structure. (12A) is one of the newer reactions that we went back and touched on in the more recent lectures. So even though sodium borohydride does not react with esters, an anhydride is not an ester because it has 2 carbonyls on either side of the oxygen. That means that one oxygen is trying to stabilize and deactivate both of those carbonyls, and it can only do half as good of a job. That means sodium borohydride is able to react. After the initial addition, we get a tetrahedral intermediate as usual, Collapse of this tetrahedral intermediate will give a carboxylate salt and an aldehyde, and we have excess sodium borohydride around. And so this is able to reduce this aldehyde that goes to a carboxy alcohol after workup. If you drew the anionic product, since I didn't explicitly list a workup, that was accepted as well. No worries. To figure out this problem, there's two things we notice. One, the product is an aldehyde. The other is that we have this very special reagent, lithium triterbutoxyaluminum hydride. This does only one thing. It reduces acid chlorides to aldehydes. So what we need to write as the starting material is an acid chloride. Someone wrote an anhydride as a potential option here, and in principle, I don't see a reason why that wouldn't work. I've never seen that reaction before. People usually don't try to use sort of these more strange reducing agents to reduce an anhydride. But I think I gave that to you anyways. But please, use an acid chloride going forward. In step C, we see we have a nitrile reacting with a Grignard. So this is going to do a nucleophilic attack directly onto the nitrile. The aqueous workup afterwards will turn this intermediate amine into an aminium, and water will hydrolyze it. After hydrolysis, we're left with just a simple ketone. MCPBA will affect a Baeyer-Villiger oxidation, and the migrating group will be the tert-butyl group because it's more substituted and it's better stabilizing positive charge. And for D, we're trying to turn an alkyl bromide into a primary amine. So this is pretty much right out of the notes. We learned a few different ways to do this. In one case, I show an SN2 substitution with sodium azide to make an intermediate alkyl azide, followed by reduction with platinum and hydrogen. You also could have used the Gabriel synthesis to effect this transformation. And we even allowed just using ammonia if a large excess was specified. So one way to get around some of these over-alkylation issues is just to use a large excess of one of the components. This actually works pretty well for something like ammonia because it's cheap, readily available, and it's a gas, or it can wash into water, so it's very easy to remove. For pretty much any other amine, you're not able to get away with this, though. (13) is a mechanism. Things we always want to note about mechanisms is what are the conditions. So we see we merely have sulfuric acid and water. That means that probably the real acid in solution will be hydronium, so it's going to be protonated water. And to get our reaction started, we have to first protonate this nitrile to make it more electrophilic for nucleophilic attack. So we see we have the protonation of the nitrile to make this nitrillium. This positive charged nitrillium is now very electrophilic. We can have neutral water attack the carbon. Then we're left with a positively charged oxygen. We can do proton transfers just to move this proton over to the more basic nitrogen. And this aminium is set up for another addition of water. Note that you can do a proton transfer on the side from here in order to get to a primary amide, but if you do addition directly into this aminium, this will actually be more productive in getting to our final answer. Addition to this aminium gives us now our tetrahedral intermediate. This requires more proton transfers in order to make the nitrogen into a good ammonia leaving group. Along the way, the oxygen kicks out the ammonia, and we have a protonated carboxylic acid that is then deprotonated either by water around, or we could be using ammonia as well. It's hard to know how fast the ammonia that's ejected gets quickly protonated by the other acid in solution versus being able to do this last protonation itself. And the final product, of course, is our carboxylic acid. Things to note is along the way we only have reactive species that are positively charged. We don't make any O minuses or things that will be very, very basic. These are elements we always want to avoid during these reactions. Lastly, we have two synthesis problems. We have this primary alcohol that we're trying to turn into an isocyanate. So when we look at this, we want to try to map on where are our carbons. So we have 4 carbons to start with. We have 4 carbons in the product. So as tempting as it is, when you see this isocyanate, this means we don't most likely want to use a courteous rearrangement unless somehow we're introducing an extra carbon in to begin with. So I believe a lot of people try to use a courteous rearrangement, not realizing that one of these carbons ends up at one of the carbons from the starting material ends up right here as the carbon, and you would actually have too few at the end of the day. So one way to do this is to turn our alcohol into a bromide with PBr3, and then use one of our many ways to turn alkyl bromide into a primary amine. You could use the Gabriel synthesis, you can use sodium azide displacement followed by reduction. This is one I like to do. And we're just left with the final problem of turning a primary amine into an isocyanate. So this is one of the reactions from the carbonic acid section. And if you have one equivalent of a primary amine and one equivalent of phosgene, the nitrogen is able to do a single substitution followed by elimination of the second chloride to give you the isocyanate. Note if you ended up having 2 equivalents of amine, this would keep reacting to give a urea. There are a few different other solutions you could do. You could oxidize this primary alcohol into a carboxylic acid, then do an amide coupling with ammonia and reduce. I think that's the same number of steps. So there are a variety of answers that we accepted. Similarly, there's another way, there's actually a variety of ways to solve this problem here. One thing that I think is the most obvious is somewhere this double bond gets an oxygen inserted into it. While it's tempting to use a Baeyer-Villiger oxidation, in the end we accepted this. This alternative where we do an oxidative cleavage of the double bond followed by esterification at the end would probably be a better synthesis that would be more selective. So along the way, there's 2 ways we can oxidatively cleave this double bond. Probably the shorter way is to use potassium permanganate to go to 2 carboxylic acids. And this gives us already one of the reagents in the right oxidation state for the coupling. Oops, I messed up. I'll fix this. I switched these around. I'm going to fix it. It's going to be great. You get to see me make my own mistake. The beauty of tablets. Then we can reduce this carboxylic acid into the benzyl alcohol that we need. And then merge the benzyl alcohol with the carboxylic acid to make the final ester product. There we go. That's better. Alternatively, you could use ozone. These reactions tend to work better. So this is the first way that came to mind for me when I thought about how to do this. And then we need to do 2 different oxidation state manipulations. We need to reduce the aldehyde to a primary alcohol. We need to oxidize the aldehyde to a carboxylic acid, and you can do the same DCC-DMAP esterification reaction. So that is all of problem set 4. Please let me know tomorrow if you have further questions. Or if you happen to see this afterwards, good luck on the test.